Welcome everybody to this month's Fire Behaviour Practitioners Network webinar. This month we have Miguel Cruz from CSIRO, who's going to present to us on the work that he and a range of other people have been doing on fire behaviour in croplands. Quite a topical area, given that we've had a number of jurisdictions have had significant fires in croplands over the last few years. So something that many of us are interested in, and how do we deal with are there differences and how do we deal with them in terms of predictive services for fires in crops before they're wrecked. So I'll hand over to Miguel. Thank you, Miguel.
Right, thank you, Mike, and let me know if this is not working. All right, thanks for the invitation, and to come and talk about the work we did last year on fire behavior in wheat crops and its prediction. And before I started, my co-authors here is Richard Early from CSIRO and Rachel Bethel from CFA. They probably put more work into this than I did. And before I start about the motivations and the methods and the results, I want to just go first to the acknowledgements of the people that made this happen. This is a project that is funded by the Safer Together program. I acknowledge the landowners. Cameron Pennycare, Rachel reached out for them, between others landowners, about the purpose and the importance of this study. And they went along despite the inconvenience of having a lot of fire disrupting their normal farming practices. So mentioned since within CFA, Alan Slipovich, Tim Wells and Tim McKern being the champions of this project and doing a lot of backstage work to make this happen in terms of being able to burn in days with quite heightened fire potential, namely in total fire ban days. Without their support of this project, we'll probably have a data set that would not be as comprehensive as the one. Other people that also help out in this project came out to the burns: Francis Ein and Andrew Sturgis from QFIS, Tom Duff and B. Tumino and Alex Filkoff from University of Melbourne, Michael Story and Alex Holmes. So these people just really did the hard work during the burns, a lot of the fuel sampling, fire behavior observations, and most important, all the fire suppression people that came and make sure that the burns were conducted safely and didn't escape any of the plots. Probably have more than 100 volunteers and other firefighters on site throughout the period of the burns. And really, they made this happen the way things happened. All right, so main motivations. Cropland fire behavior. There's approximately 21 million hectares of cultivated what we call the winter crops in Australia. Mostly are wheat, barley, and canola. So these three crops are about 90% of the winter cropland areas. And in this map, you see the dark green is the cropping. A lot of in WA, wheat belt. South Australia, you also can drive for kilometers and kilometers without seeing anything else but wheat crops. Some in Victoria as well, New South Wales, and also extending to some areas in Queensland. So quite a significant fuel. A lot of fires happening during harvesting and also after harvesting. In South Wales alone, harvesters, 7% of the harvesters in a year will cause a fire. Of these, only 10% will lead to significant damage to the machine or to the to the crop, but it's a very common occurrence, fires in these crops. As we go out of normally, or sometimes during the harvest season, there's also some, as Mike mentioned, significant fires in croplands. Some of the most notorious, Cascade fire in 2015. He made a more than 90-kilometer long run in one afternoon. It caused 4 fatalities and led to an estimated loss of about 500 million tons of grain. Similarly, the Pioneer Road fire in South Australia in 2015, very similar number in terms of final acreage in mostly wheat crops. And I believe last year was also a year with a lot of fire in South Australia in cropland areas. So there's obviously a need to predict fire spread in these fuels, and from a FBN perspective, get very accurate, the most accurate results possible. One of the questions that have been floating through time is that, well, we have grassland fire spread models developed based on fires in pastures and wildfire observations, some of them in croplands. But the big question is, how adequate are these models that we used for predicting cropland fires? Right? That was the main question of the project. Related to this is, what is the effect of key environmental drivers on crop fire propagation and behavior? From the fuel structure, but also the effect of wind and moisture content. Are crops that, because of their structure, post-harvest, are barriers to fire spread? And if there are barriers, when is that effect as a barrier will end, under which wind speed and fuel moisture threshold that would that occur? So some things we want to know. Further on, what's the effect of crop state? Croplands will go through a dynamic from unharvested to harvested as fire season progresses. Depends on the place and the market. Some of those crops might be also baled. These are all activities are changing the fuel structure, let's say, and you want to know how fire is going to behave in these different types of structures. Other question, how do you describe crops from a wildfire fuel perspective? What is really burning in the fire? Is it just a standing crop? Is that the grain is also burning? Is that the fuel or not the fuel? So just a series of questions we want to answer through our research. And for this case, we're going to focus, our initial idea was to focus on wheat, barley, and canola, the 3 most significant crop types. The approach we used was this got to burn to learn. We have been doing this with the CFA for about 9 years now. We worked with curing. We also work with fuel load, with QFEs, and also CFA. And we want to reapply the same methods that were working well with the cropland areas and cropland fuels. Rachel looked for sites in different areas of Victoria, namely more to the northwest, Bendigo area. The year we did the burns, that area was quite dry, the crops were quite poor, and we end up picking up a site south of Ballarat, this site there in the map, Wallinduc, where Cameron Care they have a farm. We prepared the area for burning for the 3 crops we were considering: wheat, barley, and canola. Unfortunately, as the fire season progressed, and you can let our burns, so this is 2018-2019 fire season, then it got too active in the end, and you're not able to do the burns in the canola or the barley. So we only did the burns in the wheat. Although I got information on fuels in the other crop types as well. So we consider 3 crop conditions: unharvested, the harvested, which you call the control, because it will be the most common condition you'll find during the fire season, and the harvest and baled condition, where besides the harvested, the biomass is harvested for baling. What we did is paired simultaneous fires. So because the wind is always changing and fuel moisture changes throughout the day, our idea was to do these paired burns, as you can see in the photo, where we're burning a control, the harvested, and one of the other plots, unharvested or harvested baled, at the same time. And so, the wind is pretty much the same. Fuel moisture is the same. The difference in fire behavior we'll observe are due to the changes in fuel structure. So that's the idea of the experimental design. And the fires, we try to do the fires under summer conditions, over a wide range of wind speeds and fuel moisture. And I will go into detail on which the range of GFDIs we burn, but we burn up to about GFDI of 70 during total fire ban days. This is our plot layout for the wheat area. You see three colors in here. The green is the control, so just harvested. The pink is the harvested plots, and then we have the harvested and baled plots. So the control is about to double the number of plots of the other conditions. This was a block of about 40 hectares we were using. We burn around, creating a fire break. And you can see, as you can see in the photo, we then went also burned the paddocks continuous to the south and to the east of the plots, just to be sure that everybody was happy and confident that the fires will not get out of the experimental area. Some of the results, just showing some of the fuel structure we had. On the top here, on the left, we have the unharvested wheat, about 80 centimeter tall, 7 to 80 centimeter tall crop. This year, the farmer considered this crop that year as an average crop. He was pretty happy. This is what we considered on the top right, the harvested or control, harvested to about 30 centimeters. So the height of the stubble is 30 centimeters, sorry. And you see some of that matted material from the harvesting. In the unharvested, there was barely any fuels on the ground. And then the harvested and bales is this central photo where you can see a much lower stubble. In this case, about 9 to 10 centimeters stubble. And that was kind of the limit of the harvester to cut and not touch the rocks that were spreading around the site that could cause fires during the cropping activity. So that's the three fuel types we had to play with. In terms of some of the results, summarizing the distributions of fuel bed height for unharvested, harvested, and baled, so around 70, 80 centimeters, about 30 centimeters on the harvested, and about 9, 10 centimeters on the baled condition. Fuel loads, about 5.5 tons per hectare for the unharvested, the standing biomass without the kernels. On the harvested, is about 2.3 tons per hectare, and on the baled, it's slightly lower than 2. It's about 1.6, 1.7 tons per hectare. And this is the standing biomass. We also sampled the matted biomass you saw in the photos, but they are not in this graph. Just as reference, a natural grassland in this area, ungrazed, would be a fuel load about 4.5, 5 tons per hectare, so somewhat below the unharvested crop, but above the harvest condition. I'll show you now a video of one of the burns. So the plots are 50 by 50 meters, and we have been, before these experiments, we're doing 33 by 33 plots. In this case, we decided to go a bit larger, although the size of the ignitions is the same. We just allow the fire to spread for a bit longer. So ignition is always a little bit of a problem in terms of we need to allow fire to build up. And you only start to make the measurements of fire behavior after we attain a parabolic at fire shape. And that's kind of the last 2/3 of the plot. So about now, we have this shape here on the fire, and that's when you start to make the measurements of fire behavior. So this is the unharvested condition. You see quite deep flames, about a 10-meter depth on the flame front. Quite tall flames, 3 to 5 meter tall flames. And that's it for fire. Quite quick spreading fires. So this is the unharvested, just an example. So you have these UAVs or drones above, stationary, and they just get the perimeter of the fire. It evolves for us to then measure fire behavior. I'm just going to show you a quick contrast between fire behavior observations in the control, unharvested, and baled for 3 fires burning in very similar GFDI. So between 27 and 28, wind speeds around 30, between 30 and 26 kilometers per hour, fuel moisture between 6 and 7% moisture content, right? And that's again, top view of 3 plots. We have on the left the control, middle the unharvested, and the baled on the right. So 5 seconds after ignition, after the first drops of fuel on the line ignition. 15 seconds after ignition, you start seeing the unharvested building up quite quickly, followed by the control, and the baled condition, much more broken flame front. 25 seconds, sorry. You see just that parabolic shape in that fire in the unharvested. The control is not there yet, spreading a bit slower. You also see difference in flame depth and the color of the flames. And in the baled, still building up. 35 seconds after ignition. And patterns, in this case, the control already attained that parabolic shape. 45 seconds after ignition, you see the fire reaching the edge of the unharvested plot, still going the other 2 plots. And for this 27, 28 GFDI, that's the final shapes of the fire and the time the fire took to reach the end of the plot. So 45 seconds unharvested, 55 seconds in the control, and 95 seconds on the baled plot. In terms of rates of spread, and these rates of spread are not for the full plot, they're only for the second 2/3 of fire propagation. The control had a rate of spread of 4.3 kilometers per hour, unharvested 5.8 kilometers per hour, and the baled plot 2.2. So almost 1/3 in these conditions than the unharvested, independent of the weather conditions that were essentially the same. So all these differences are effect of fuel structure. In terms of flame heights, observed 1.5 to 2 meter in the control, 3 to 5 meter in the unharvested, so more than the double. And for the baled, less than 0.5 meter, so almost 1 order of magnitude less than the unharvested plot. And this is clear also in these are 2 other fires, GFDI, very similar, 26. And you see these poles here in the harvested and baled. There are similar poles here, the same scale, essentially. You don't see them because they're hidden under the crop mostly, but you see the differences in flame heights as the fire coming out of the plot between the unharvested and the baled condition. Quite significant differences. Now, some fuel consumption features that we also learned from our burns. This image on the left is a fire spreading on the baled condition. You see this, you see the edge of the fire here, but you see also some white lines within the flame front. So what was happening here is that the fire is being carried by the standing stubble, the 9-10 centimeter stubble, but is not consuming any or charring any of the fuel, of the matted fuel. And so this takes about 5 meters behind is when you start seeing these fuels start to charring and releasing volatile that will contribute to the flames. So that's just telling us the matted fuels in this crop, and this was visible in the harvest condition, was not visible because the flame was denser and it couldn't see through it. But what you're observing is the matted fuels are not contributing to fire propagation. They're being consumed way behind the leading edge of flame front. Also, we observed in these furrows, in the plantation, a lot of the fuel didn't get consumed. Some of that got charred, and if you dig in these furrows, you'll see fuel that didn't even got charred. So again, some of that matted fuels that at time for the baled condition was about half the total fuel load. If you harvest all the biomass, half of that fuel was not being consumed by the fire. We think what happened was that the strong winds were cooling the fuels behind, and extinguishing the fire was quite behind the leading edge of the flame front. Another thing we didn't see burning was the seed heads. There was also questions, are the seed heads fuel or are they not consuming the fire? And what you observed was the seed heads were not consumed in these intense fires in unharvested crop. We also didn't observe them to be a spotty material in our fires. It can be that in more intense fires with wider flame fronts than what we observed, namely in a wildfire, some of these will be transported by the turbulence. And they're quite heavy, but they definitely can cause spotting over roads and other areas without fuels. So look at some of the trends in the data. We did 55 burns. 10 of them were not used because of issues with ignition failing, and not creating that nice fire shape we wanted, or changing the wind speed. So that left us with 45 fires for the analysis. Some of the data extremes we had a GFDI up to 71, average open winds, 10-meter winds up to 40 k's an hour. We had gusts about 55 k's an hour at times. Moisture contents down to 5%, and the maximum rates of spread up to 10 kilometers an hour. Now you see here the distribution of the GFDI for the 3 crop conditions. No really significant differences. The way we were burning was we're burning paired burns, and we were harvested and baled burn be followed by unharvested and harvest burn. So we kind of mixing the burns quite a fair bit. So we have no difference in GFDI, but when you start looking at the difference in fire spread, you start seeing significant differences with the unharvested fires spreading much faster than the harvested, and then much faster than the baled. These differences become larger when you look at fire line intensity, with unharvested averaging about 20,000 kilowatts per meter, where the baled averaging about 5,000 kilowatts per meter. So quite significant difference in fire behavior between the different crop conditions. And here also flame height differences, just to provide an image of what I showed before. Now, so one of the things we want to quantify, so these paired burns, what exactly is the difference between fires burning in the different conditions and the same environmental conditions, different fuel conditions, same environmental conditions, right? In this plot, we have the differences between the treatment and the control, each point here. In the blues, we have the unharvested minus the harvested, because unharvested tend to be faster, or we're always faster. All the data is above the 0 line, where we know the difference between the treatment, the harvested or baled, and the control. And we have the baled and the harvested red dots, they're all below the 0 line, right? This is meters per minute. 50 meters per minute is 3 kilometers per hour, right? So you can see the range of differences in terms of rates of spread we were obtaining in our fires within this range of GFDI between about 15, in this case, to about 60. For this range, what observed, the unharvested conditions fire spread on average 2.1 kilometers faster than the harvest condition, and the harvest and bale spread also 2.1 kilometers slower than the harvest condition. Very interesting coincidence that the values are very, very similar to each other, independent of the difference in fuel structure. So we see some, this is for rate of spread in terms of flame heights, same patterns. This is in meters. Again, flame heights on the unharvested crop tend to be about 2 meters taller than the harvest crop, and the baled condition tend to be 1.2 meters shorter than the harvest or the control crop, right? Significant behavior changes depending on the crop condition. Now, one of the other things we wanted to know, or in fact, the main objective was to know how the current models predict fire propagation in these crops. And do we need new models that describe fire spread in cropland areas, and for wheat? In these graphs, these panels, we have the natural grass model, the grazed grass model, and eaten out grass model. And you have the observed rates of spread versus the predicted. So we have the line of perfect agreement in each graph. And so for the natural grass model, what you observe is the red dots that are the unharvested crop are really around the line of perfect agreement, bit of spread, that's expectable, but there's no bias. And so the fires follow the line of perfect agreement. Whereas for this model, for natural grass predictions, the harvested and the harvested bale are mostly, not all, on the bale condition in the over prediction range. So the natural grass model is essentially over predicting fires in harvested and harvested bale crops, but are doing a good job in the unharvested condition. You go to the grazed grass model, and what you get is a shift. So the unharvested start to be under-predicted, fires in unharvested condition. The fires in the harvested condition get a better fit, whereas the fires in the baled condition are still being over-predicted, I'm sorry. You go to the eaten out grass model, and you further shift with unharvested and harvest fires all being under-predicted and a good fit for the baled condition. So if you just consider that correspondence between the natural grass model being used for unharvested crops, the grazed and cut grass model being used for the harvest wheat crop, and the eaten out grass model used for the baled crop, you get this graph of observed versus predicted rate of fire spread. Most of the data within that plus or minus 35% range. In fact, the errors were quite low. Some of the lowest we have been finding in our experimental studies. As a percent, the error was 22 to 25%. Right? If we use the data we try to develop the models, a model for rate of spread in these crops, we will not get errors as good, as low as this one. So this seems to be a good match between the models and the crop condition in wheat. Now, most of our fires were in we think to ourselves, how is this going to translate, all these models corresponds to going to translate when you go to much higher GFDIs, right? And because they also talk about the effect of fuel structure diminishing as severity of burning conditions increase. And there's not much data out there for that, but there's some evidence from a few fires. In this case is the Cascade fire 2015, and Neil Burrows did a reconstruction of this fire. Again, about the 94-kilometer run in one afternoon. GFDI for this fire was above 150 for a period of over 3 hours, peaked to 222, mostly fire spreading in unharvested wheat. What Neil Burrows concluded was the observed rate of spread was about 14.4 kilometers per hour. And he did some simulations with the Grass model, Grass model, and he obtained a 15.8 kilometers per hour for this fire, for these conditions. There's 3 weather stations surrounding this very, very long fire. This is a level of over prediction of error of 9%, which is quite good. Now, one thing you'll notice is that in this case, we're using the Grass model for unharvested crop, whereas earlier I was saying natural grass or ungrazed grass model for the unharvested, right? And only the Grass only for harvest crop. And also, I would like to talk with Simon Telfer for the Pioneer Road fire. He got a really good agreement running Phoenix with a fuel load of 4.5 tons per hectare, which is the rate of spread given by the Grass model. The Pioneer Road fire also running under very high GFDIs and in mostly an unharvested wheat crop. So very similar results to what Neil Burrows mentioned in his study. Now, if we go back to this graph I showed here, I showed this graph here, which shows the absolute differences between the different conditions. But if you consider relative effect, where you have the treatment minus control rate of spread divided by the control, we see that as the GFDI increases, the line, the trend line trends to approach zero, tend to decrease the range of these differences and approach zero. And as a matter of fact, this line here between unharvested and harvested would reach zero at a GFDI of about 125. The line of the baled and harvested would be a bit further down the GFDI range, let's say. So what we're observing is that with this experimental data set and with extrapolation observation for the wildfires, is that the difference in fire behavior between crop conditions seem to decrease with increasing GFDI. And it goes back to that idea, as weather conditions and fire weather becomes more extreme, effects of fuel tends to decrease. And that's observed also in the crop fires. So some just concluding take-home messages. We try to focus on the results from an F-band perspective, but I guess also from the fire behavior to observe differences. There's also implications for farm management. So we notice quite significant differences in fire potential and spread and flame heights, and the difficulty of suppression for the various wheat crop conditions. And it's a question I put here: can these be applied in farm management? As summer comes, can you, as a farmer, do your harvesting, locate your harvesting within our property in areas that will lower the potential that if you have a fire, will lower fire propagation. And only if you have a fire, that's caused by your machinery, and lower the potential of that fire propagating through your estate and other estates. We found a direct correspondence between fire rates of spread in 3 crop conditions and the outputs of the CSIRO grass fire spread models. Again, unharvested wheat, natural grass fire spread model, harvested wheat. In our case, it was about a 0.3 meter tall stubble, used the great grass fire spread model, and baled wheat, about 10 centimeter tall stubble, used the eaten out grass fire spread model. This for the normal range of GFDIs, but when you go really to extreme range, this effect is going to be diminished, and probably better maybe use just the grace model, or if it's unharvested wheat, if unharvested wheat, use the natural grass model and live with a bit of more of an overprediction. Overprediction never too much of a problem in days that we have GFDIs above 100. Notice here also error is quite good, between 22 and 25, so, and no very reduced bias. So pretty happy with how the models are predicting fire propagation in weeds. And before I conclude, I would just like to show 2 more slides. One brings this issue of the gap to burn to learn. We have been using, before we start our burns, we were asking everybody who was participating on the burns, what was their perception, what fuel type would result in the fastest fires, right? So we had the unharvested wheat, the harvested, we had the baled, and also considering a hypothetical fire on a grass, a natural grass fuel. And as expert opinion, I think we had about 20 to 30 people answering this question. Most of the people said the fuel type resulting in the fastest fires was the harvested crop. Whereas we observed unharvested crop to have the fastest fire. I myself, I went for the harvest choice in this case. And in terms of what fires would be the slowest fires, expert opinion said that majority unharvested said that the slowest fires will be the unharvested condition, followed by the baled, which was the correct answer. So let's just reiterate that need that we got to burn to learn. We learn by observing fire, by hearing stories, but sometimes we can't extrapolate findings from certain fuel types to other fuel types, right? So the importance of this approach to do research on fire behavior. And just a notice here, we put some publications based on this data. If you are interested in reading them, just flick me an email. I'll send them. It's all published in the National Journal of Wildland Fire. One is about what the results I just showed here. Others are commenting on some other research findings that and contrast those with our findings. And just to finish here is where are we going to the future? So future work, I think in doing, one aspect is as we sample the canola, that photo here is a canola crop, a post-harvest canola crop. We know there's barely any fuel, and even the fuel that's there standing is quite coarse. So there was raising the question how our fire spread in the canola is canola a fire break, canola post-harvest canola paddocks or areas of fire break, or are they allowed fire to propagate? Under which conditions is going to fire really spreading this in these fuels? So that's something we aim to do in the future, and also go back to the barley. The barley is also very similar to, in terms of structure, to the wheat, but you want to just make sure we are. By observing fire behavior, we have the right assumptions about fire spread models and crop conditions. As we observe also this notable difference in fire behavior in different crop types and conditions. We start asking ourselves, can we better map crop condition and crop type from remote sensing, and start producing landscape maps that show that evolution as we do with curing through the fire season. We also see the change of the landscape as the fire season or the cropping season progresses, and start to have that as a map and obtain more accurate predictions when you use softwares like Phoenix or Spark in the future. And yeah, the final aspect here, a few years back, we put up a guide for constructing cropland wildfires, a project with CFA and the Bushfire CRC. And the idea is to agencies to document crop fires, obtain data that can be later used for further validation of the models. We are still waiting to get some more data from the agents about that, and kind of expand the analysis to more data in that extreme end of the data set. So that's all I had for presenting here. It was already a long presentation, and I'll be happy to take some questions.
Thanks very much, Miguel. There's a lot in that we'll need to think about, and some really good work in terms of advancing our understanding of fire behaviour in crops. Does anybody have a question for Miguel?
Yes.
Go ahead.
G'day, Mike and everyone. Andrew Sturgis. Miguel, how you going? Got a few questions. Can you hear me, Miguel? Frozen on my screen.
Oh, God. Yes, I can hear you.
G'day. The ignition protocol. So it was a 50-metre plot, but you only ignited 33 metres. Can you talk about that a bit, please?
Can you repeat, please?
Yeah, your ignition protocol, just the setup of the experiments. They're 50-metre plots, but you obviously didn't light the whole 50-metre edge.
That's correct.
Why was that?
We wanted to be consistent with the previous burns we did. And so that on previous burns we did on grasses. That also allows to combine data sets. That's reason number one. Reason number two is that we found, even before this study, that those 33 by 33 fires, they were being predicted without a bias by the models that were based on larger experimental fires and wildfires. So that was hinting us that those burns were essentially capturing the effect of the environmental conditions on fire behavior. One thing we did more now with this data set, because we went into more detail, we have longer plots, and we went into more detail into measuring rates of spread. And that's one of the papers we were talking, I showed over there, the effect of the ignition land and that size. Is that enough to provide a fire that is spreading at steady state? And we found out through our analysis that it doesn't matter if you are at early stage or early, let's say up the plot or late in the plot. We have three areas where you measure rates of spread, and we don't find the bias where the fire will be still accelerating by the time you exit the plot, right? Another thing we did in these burns was, you might recall in the earlier image with the plots, there's two large plots. They are 100 by 100 meters. And once we ignited those burns and compared those with the 33 ignition lines, we didn't see a So essentially, there was no need to go for larger ignition lines.
All right. Thanks for that. I might talk to you about the 100-metre ones later. I was one of the experts, I think, that got it completely wrong. So could you talk about why we got that so wrong? So we thought that the lower fuel loads, the harvested crops, would spread faster than the unharvested, which is what happens in the natural grasses, yeah.
Yeah, so I think people might got it wrong because of different assumptions. There was a trend that the more experienced people got it wrong than people with not much experience, right? And in relation to the findings we got from the grass fires, the thing is that the heavy fuel load. So if you remember, the effect of fuel load in grasslands was found to, as fuel load increases, rate of spread is going to increase up to about 6 tons per hectare, and only when fuel load increases to the 10 tons per hectare, when really high fuel loads, that's when you start seeing the decrease in rate of spread. The crops, these crops were on the upper range, on the earlier range of fuel loads, right? So about the 5.5 tons per hectare. So the crop, although it's heavier, but is not in the extreme end, right? The other aspect, aside of fuel load, is the fuel bed height. Fuel bed height was not changed, it was pretty constant on the grass fires that we carried in the past. Whereas here was very notorious changes in fuel bed height. And as the fuel bed decreased, so that the rate of spread decreased. So that's kind of, that's my take why we are not observing the same impact in these crop fires that we saw in the grass fires. Essentially, we are not up in the high end of the grass fuel loads.
Coarseness of the fuels?
Well, coarseness of the fuels here were pretty constant because the same species, right? Here is really tricky in terms of coarseness because there's the leaves and there's the stalks that are hollow. But the leaves and stalks were definitely coarser than what you observe in a native grassland, right? Those fuels tend to be thinner.
All right, I'll just ask one more. So, and you did touch on it in maybe your last slide about remote sensing. So we've got a good fit with the various existing grass fuel models, the eaten out, grazed and natural, but knowing when to use which model. So there is some work being done in remote sensing. I'm wondering, how we know which one to apply when.
Yeah, so that's something that's a bit of a move inside with Richard Early and the remote sensing people trying to look at that. I know there's other people, other work elsewhere just on crop identification, but you want to get into the crop status. So even if it's wheat, you want to know if it's unharvested or harvested, and can you even get more than that? Right, so that's something that there's the idea of starting that as future work, not done yet.
Be keen to know how others are thinking they're going to apply your findings, and thanks very much, Miguel. That's me.
Thanks, Andrew. Some very relevant questions. Just a reminder to those who aren't, if you're not speaking, to mute yourself because we are recording this. Are there any other questions for Miguel? I'll wait for a couple more minutes. Otherwise, it sounds like there's no more questions other than an open-ended one that Andrew has sort of started on in terms of how do we now go and work out what state various bits of the landscape with crops are in. I know there's some work in the agricultural sector to work out which crops are where, but I don't think they go to the level of what's harvested and what hasn't been. So that's something we may need to explore with some other partners, as well as Richard. If there's no other questions, I won't hold people up much longer. Thanks very much, Miguel. That was a really thorough and informative discussion, and I certainly look forward to some further discussion on how we better integrate this into our existing practices and systems, because we certainly appear to be having more crop fires, or more bigger crop fires than we used to have. Thanks very much, everybody, and for those in Victoria, stay happy and well, and for the rest of the world, just stay healthy. Thanks very much.
Cheers.
We'll leave it there.
Thanks, Mike.
Thanks very much, Mike.
No, thank you, Miguel.
Talk soon. Stay safe, everyone.